In the last video, we sorted sample spaces into three families: finite, countably infinite, and uncountably infinite. This short coda ties off two topics that complete the picture. First, the continuity of probability, the fact that probability behaves well under limits when a sequence of events steadily grows or steadily shrinks. And second, a glimpse of measure theory, the honest answer to a question the continuous case forces on us. Can we really assign a probability to every subset of the sample space? Start with a sequence of events that only grows. A1 sits inside A2, which sits inside A3, and so on, an increasing sequence. And we write A for their union, the limit they fill out. Picture nested regions, each containing the last, expanding toward A. Continuity from below says exactly what you would hope. The probability of the limit is the limit of the probabilities. PR of A equals the limit, as n goes to infinity, of PR of A minus n. Why is it true? The trick is to disjointify. Let B1 be A1, and each later BK be the new ring that AK adds to AK minus 1. These shells are disjoint, the first n of them union to exactly AN, and all of them together union to A. Now apply the third axiom, countable additivity. PR of A is the infinite sum of the shell probabilities, which is the limit of the partial sums, which is just the limit of PR of A n. The axiom of countable additivity is doing all the work. The mirror image holds for a sequence that only shrinks. Now A1 contains A2, contains A3, and so on, a decreasing sequence, closing down onto their intersection A, the part common to all of them. We do not need a new proof. Flip to complements. As the AK shrink, their complements grow, an increasing sequence we already understand. Apply continuity from below to the complements, then use the complement rule to flip back, and out comes the same conclusion. PR of A equals the limit of PR of AN. Continuity from below for growing events, and continuity from above for shrinking ones, together go by one name, the continuity of probability. It is what lets us pass to the limit, to talk about what happens eventually, not just at every finite stage. One last honesty. Our intuition for the infinite climbs a ladder, the finite we grasp directly. The countably infinite, the integers, the rationals, we can at least list one element after another. The uncountable, the real numbers, cannot be listed at all. There are strictly more of them. We use the finite to understand the countable, and the countable to reach for the uncountable. Now the catch. It is tempting to assign a probability to every single subset of the sample space. For a finite or countable omega, fine. But for an uncountable omega, this leads to genuine contradictions that cannot be patched. You simply cannot weigh every subset at once. The resolution is to step back and only assign probabilities to a well-behaved subcollection of events, closed under complements and countable unions. Such a collection is called a sigma field, and the events in it are the admissible ones. Studying sigma fields and the measures defined on them is the subject of measure theory. And measure-theoretic probability gives one unified framework for the discrete and the continuous alike. We are only pointing at the door here, not walking through it. And that completes the probabilistic model, a sample space of outcomes and a probability law that obeys the axioms and respects limits. Everything in the rest of the subject is built on this foundation.